everyone, this is going to be a video walkthrough of Spring 2021 CS61b Midterm 2 question 5b. So for this question, we are, for this first question in 5b, we're given a 2-3 tree of height 6, and we want to figure out what is the minimum height for its corresponding LLRB tree. So note here, how we define height is as the number of edges from the root to the furthest leaf. So giving an example, if we have a tree that looks like this, then the height will be 2 because if it looks like this, okay, because the furthest leaf to the root has 2 edges in between. Okay, cool. So knowing that, to figure out what's the minimum height for the corresponding LRB tree, let's recall that when we convert a 2-3 tree to an LRB tree, we essentially add a red link for any nodes that are, for any items that are stuffed in the same node. Essentially, if we have a node that has 2 items, we insert a red link here. So when we convert it to its corresponding LRB, we'll have +1 with the height, because we +1 on the number of edges from the furthest leaf to the root. Okay, however, in first question, we want to figure out the minimum height. So in that case, we don't want to increase our height. And essentially, this will be the case when we have no items that are no more than 2 items in the same node. Essentially, the B tree will be reduced down to a normal binary tree so that when it converts to its corresponding LRB tree, we don't increase the height at all. Okay, so looks something like this, but with height 6. So in this case, the height wouldn't change at all when we convert it to its corresponding LRB tree. So the first answer is 6 for 5b. Okay, cool. So for the second question, it's quite similar, but the opposite case. We want to figure out a 2-3 tree of height 6, what's the maximum height of its corresponding LLRB tree. So in this case, because we want to increase the height as much as possible, in order to increase the height, we want to think about a case when we need to insert as many red links as possible. So in this case, we want to assume all the nodes that's from the path from the root to the furthest leaf, all the nodes there will have multiple elements in the same node. So that in that case, we can insert red links in all the nodes that we go through when we count the height. Okay, so now to figure out exactly how many red links we can insert, we first need to figure out how many nodes are in the longest path when we have a 2-3 tree with height 6. Okay, it's really hard to draw an example with height 6, so let me draw like a smaller example so that we can see what's the pattern when figuring out the correspondence between height and the number of nodes in the longest path. So when we have height 1, it will be the case when there are 2 nodes in the longest path. And when we have height 2, it will be the case when we have 3 nodes in the longest path. So hopefully from these 2 examples, you can see that when we have a height 6, 2-3 tree, the longest path will have 7 nodes. Okay, essentially there will be 6 edges in between, but 6 edges will connect 6 plus 1 nodes. Okay, so given that, we can calculate how many edges or how many total number of nodes are there when we count from the root to the furthest leaf. Because we want to maximize the number of red links, we want to, let me change this to a height 6 example. We want to make sure every node in this path have the maximum number of elements possible that we can stuff in the node in a 2-3 tree. Note that in a 2-3 tree, the max number of items per node is 2. Because when we reach 3, we need to split the node and pop up the middle node to its parent. So in this case, because we have 6 plus 1 nodes, we have 7 times 2 items in total in the furthest, the longest path. And because we have 14 items, we'll have 7 times 2 minus 1 edges in between these. These include 7 red links and 6 black links. Okay, so the answers for question 2 will be 13 because we'll have 14 maximum number of items in the longest path, and we'll have 13 links connecting these items. And there will be 7 black links and 6 black links and 7 red links. Okay, sounds good. So now let's try to work on question 3. Okay. So for question 3, we want to figure out what's the minimum possible height when we have a 2-3 tree with 8 values. Okay, so note that this question didn't really give us specific values we need to insert to the tree. So we can think of, we have all the integer possible, which is infinite number of integers we want to insert in the tree. So a key to this question is to really not worry about what specific values you're inserting to the tree, because whether you want a smaller value or a larger value, there will always be one that exists you can insert to the 2-3 tree. So we don't really have to worry about the specific values. Okay, so in this case, we want to figure out what's the minimum possible height. So in order to make the height as small as possible, we want to minimize, let me write it in red, okay? We want to minimize the number of splits and pop-up operations in constructing a 2-3 tree. So in this case, let's try to kind of draw out the tree and see how we can try to minimize the number of split possible. And the key to note here is, in order to minimize the number of split and pop, we want the items to be spread out among all the nodes as even as possible, so that there's no one node that reaches 3 items that quickly, so that we don't need to split that node. So for question 3, let's start with first element, pretty basic case. So we have insert the second element that has to be attached to just this original element we have. And because we only have one node, when we insert a third element, it has to stuff with the original 2 items we have. So in this case, we reach 3 items per node, so we need to split it. So we pop the middle element up to the parent, okay? So in this case, we need to be much careful because there are 2 places we can insert to, the left child or the right child. And because we want to make all the items to spread out as even as possible, for the first element, let's randomly insert it to one of the side. So when we insert the 5th element, we want to insert it to the other leaf node, so that we don't really insert it to here, so that we don't really need to split any node or pop up any node, okay? So now we have 5 elements in our B tree. So now we have to insert the 6th element. And we can see that no matter where we inserted either the left child or the right child, either way we have to split the node and pop it up. So in this case, we just need to randomly insert it to one of the side. And let me just choose the right side in this case. So we need to split the nodes and insert it to pop the middle element to the parent and split the node. Okay, so now we have 6 elements in our tree, and now we need to insert 2 more. Note that if we insert it to this node with 2 items already, we need to split and pop the middle element. So we don't really want it here because we want to minimize the number of split operation as much as possible. So in this case, when insert the 7th element, we insert it to this node where we don't really need to split yet because there was originally just one item in that node. And when we insert the 8th element, we want to insert to the other node that only has one item left, so we don't need to increase the height. So for question 3, the minimum possible height we can achieve with 8 values in a B tree will be 1, because this is a maximum number of edges, or this is a number of edges from the root to the furthest leaf. Okay? So for the 4th question, we want to figure out the opposite case. What is the maximum possible height when we have 8 values in the 2, 3 tree? We do a similar approach compared to question 3. However, one thing is, instead of minimizing the numbers split, we want to maximize the numbers split and pop operation, because we want to increase the height as much as possible. And to do that, we want to basically stuff all the node so that it split as quickly as possible. Okay, we want to stuff one node so that we split as quickly as possible. So let's draw an example to figure out question 4. So first we start with a single item, and for inserting the first 3, there's nowhere else we can insert, so it has to result in a tree that looks like this. Okay, so when we insert the 4th item, either way, either we insert it to the left or the right, it's the same case because both of them just have one item per node. So let's just insert it to the right here. Nothing happens because there are only 2 items per node in this case. When we insert the 5th item, note that in question 3, we'll insert it to the other node where there's only one item because we don't want to split. However, in this case, we want to split as often as possible. So we will insert it to the node that has more items per node in this case. So it will be here. And note here, we already have 3 items per node. It's time for us to split and pop up the middle element. So we'll erase the middle element and split the leaf. Okay, so now it comes down to the time to insert the 6th element, and because all the 3 leaves have just one item per node, it doesn't really matter where we put it because it will result in a similar case. Nothing will happen because there's nowhere we can split. So when we insert the 7th element, we want to insert it to the node that has the highest probability of splitting, which is this node with 2 items per node. So we'll insert the 7th element here. In this case, we split the middle element, pop it to the parent. And note that after we split the element and pop it up to the parent now has 3 items. So we need to recursively split and pop up elements from the parent node. So in this case, it will be erasing the middle element, pop it up to the parent. So the resulting tree will look like this. Now it comes to the time when we insert the last element, the 8th one. And note that here we have all 4 leaves as just one item per node. So no matter where we insert it to, it's impossible for us to pop up element and split the leaf. So in this case, it doesn't really matter where we insert it to. It will be similar cases where we just insert it and there's no splitting and popping up that can happen. So in this case, question 4, we count the maximum number of edges from the root to the furthest leaf. In this case, it will be 2. So the answer for question 4 will be 2. Okay? Cool. So now let's try to figure out question 5. And this question asks us, what is the maximum number of nodes we can insert into a 2-3 tree created in question 4 without increasing its height? Okay, so there's a warning that this question is quite challenging, because if you really try to work out this question by hand and by drawing out the tree as we did in question 3 and 4, it will be quite difficult because there are just so many items that we can insert, and there are so many split operations that can be done. Okay, so now I want to kind of demonstrate a mathematical way to figure out this question. Because we don't need to really think about like specific values in this case. We can just think about this question in terms of what's the maximum number of items a 2-3 tree with height 2 can hold, because we want to work it out based on the answer from part 4. The height is 2. So a good thing to figure out is what's the maximum number of items we can insert to height 2, 2-3 tree. Okay, and in order to maximize the number of items in a 2-3 tree, we want to stuff all the nodes so that every single node holds the maximum number of items it can hold. And we want every level to be complete in the sense that we want all the children to have a node there. We don't want any node to have no children when it can hold more than one nodes. So in this case, when we draw the tree, because every single node in a 2-3 tree can hold maximum 2 items, and so the maximum number of children per node in the 2-3 tree will be 3. Okay? Because we want to maximize the number of items, every single child should have 2 items per node. And the same thing should apply to, okay, let me draw out better. So let me spread it out a little bit. So for the second level, we'll also want the same thing to happen because we want the maximum number of items in the tree. So in this case, similarly, sorry, this is not a really good drawing, but hopefully the idea is here. Okay, we want the tree to be complete, and we want every single node to hold maximum number of items it can hold. So this will give us a 2-3 tree that has a maximum number of items it can hold. So let's kind of calculate it. So we can see that from the first row, we have one node that has 2 items. In the second row, we have 1 times 3 node, and every node holds 2 items. And at the last row, we have 3 times 3, because every node in its parent level can have 3 children, so it has 3 parents. In this case, it will be 3 times 3 nodes in the child level, in the bottom level, and every node can have 2 items. So in this case, the equation reduced down to 1 plus 3 plus 9 times 2. Okay, so this give us, this will be 13, give us 26. So 26 is the maximum number of items a 2-3 tree with height 2 can hold. Okay, however, for this question, it asks us what's the number of items, number of nodes we can insert, number of items we can insert to the 2-3 tree created in 4. I believe this question is asking us the number of values. Okay, this is an outdated PDF. So this should say the number of values. Okay, so this question asks us the maximum number of values to insert to whatever we have in question 4 without increasing its height. And note that question 4 already have 8 values. So in this case, in addition to what we have in question 4, we can only insert 26 minus 8, which is 18 values. Okay? So in this case, don't forget to subtract the 8. So in this case, the answer for question 5 will be 18. Okay, so this concludes the walkthrough for question 5b in midterm 2. Thank you all for watching.